So I have a series here, and I want to think about where this series converges, specifically for what values of r does it converge. And this is a special series, right? It's got a name. It's called a geometric series. Uh, the individual terms of the sequence here, each one is formed by multiplying the previous one by r. Right? So the first term is ar to the 0, ar to the first, ar squared, ar cubed, and so on. So how can we figure this out? Well, first I'm going to look at a couple of special cases, which are going to end up being our edge cases. When r is equal to 1, the series is just the sum n equals 0 to infinity of a. 1 to the n is 1 for all values of n, which means my partial sums are a, 2a, 3a, 4a, 5a, 1000a, a million a. That's pretty clearly diverging. Right? So the series does not converge when r is equal to 1. Okay, well, how about negative 1? Well, negative 1, we've also got a problem. Right? When r is negative 1, this is the sum. And that negative 1 to the n, it just flips back and forth between 1 and negative 1. When n is 0, it's 1. When n is 1, it's negative 1. When n is 2, it's positive 1 again, and so on. So the partial sums, s sub 0 is a, s sub 2 is a minus a, which is 0, s sub 3 is 0 plus a, which is a, and we're just flipping back and forth, right? It's never going to settle down and converge to anything. So the series also doesn't converge when r is negative 1. Okay, well, how about when it's not one of those two values? Okay, well, what's the nth partial sum? Well, it's a plus ar to the first plus ar squared plus so on out to ar to the n. Right, so here's what I'm going to do. I'm going to multiply both sides of this by r. Right, if I do that, the right side is r s to the n, r s sub n. And on the right side, the exponent just increased on every r. Right, so we've got a to the ar squared, ar cubed, all the way out to now a r to the n plus 1. Okay, now I'm going to subtract these two from each other. Right, I'm going to do s sub n minus r s sub n. So it's the top one minus the bottom. Right, so now think about what happens here with these terms. I've got a, then I've got a sub r minus a sub r, that's 0. I've got ar squared minus ar squared, that's 0. Everything is going to cancel all the way out to that a r to the n plus 1, which doesn't have a match in the first sequence. So what I'm going to be left with on that right-hand side is a minus ar to the n. Okay, take that left-hand side, factor out s sub n, right? We get s sub n times 1 minus r, divide both sides by that. Right, so move that 1 minus r over to the right-hand side, and I factored out the a from the numerator. So I've come up with a formula. Right? It's kind of what we've done several times before. I've come up with a formula for s sub n, the nth partial sum, in terms of the three parameters, a, r, and n. So now what I want to do is I want to take the limit. Right? What is the limit of the partial sums? If that converges, for whatever values of r that converges, the original series is going to converge. So I did a little arithmetic, a little algebra here. I factored out that a over 1 minus r. There's no n's anywhere in there, right? So that's a constant as far as the limit is concerned. I went ahead and pulled it out, right? And now we really kind of need what we have to answer the question. I'm going to move the limit inside. The limit as n goes to infinity of 1 is just 1. And that limit there on the right, the limit is n goes to infinity of r to the n. This is something we've seen before. When the absolute value of r is greater than or equal to 1, that's going to diverge. If it's 3, for example, then it's 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, right? It's going off to infinity. And when r is between negative 1 and 1, that's when it's going to converge. It's going to go to 0. Right? So that gives us our final result. Right? Here's my final conclusion. The sequence converges when the absolute value of r is less than 1. diverges when the absolute value of r is greater than or equal to 1, and when it converges, that's what the sum is equal to. So if you'd like to get the full context, you can click on one of the links down below here. That'll take you back to the original lecture. And if you click on the other link, that'll take you to the next lecture in the series where we start talking about developing some tools that we can use to determine when series converge and when they don't. And of course, if you like this example, please don't forget to click on that like button down below as well.